The work I'm presenting here is done more or less entirely within Ashley, so it's a direct Ashley outcome, so to say. I'll skip these. First of all, a bit about the background. This research was done by university, so I'm a member of the Hamburg University of Technology, of the Department of Aircraft Systems Engineering, and we are situated in Hamburg, in Germany, just besides Airbus. It's rather small institute compared to others, so we have 6 technicians and 25 research engineers working on different topics, mainly in the field of aircraft systems. And of course, nowadays you don't have any system without avionics, so it was decided, well, years back, meanwhile, that of course avionics is just logical to tackle with respect to systems. We have facility on the right-hand side, you see it in the picture, also to drive large test benches up to TRL level 5. So it has been there for many years, just that you have a brief idea about where I'm coming from, what the background is. What is the goal within Ashley? Well, within Ashley we are more on a tool side, so more on a software side, and more precisely we are providing one of the tools that build the, let's say, seamless tool chain we are focusing on within Ashley. So it means that during the development of avionics you have many different tools in different areas with different aspects, and they are slightly sketched here. These are the tools that are all being used in the Ashley project, and well, the goal is here to try to harmonize those tools by means of that they can actually share the information they are bound to with each others, which is mentioned by the arrows. You have to be aware that these tools are usually from different suppliers in the end, so they are module suppliers and function suppliers and so on. They all have different tools, so the interfaces become really an issue. And one of the tools we are responsible for is the platform configuration tool, and that's what I would like to talk about in my speech. It's situated in the middle, and you see we have quite some interfaces to other tools, which is challenging. So I'm talking about this. What are actually the challenges in the so-called configuration process? Well, in the end, you have many thousands of configuration parameters, and they are very different. So there are hardware and software dependent parameters that actually set up what resources you're going to use on a module, how you use the resources with respect to schedules, task, memory, and so on. And you have different phases in the development process. You have, for example, the phase where you develop hardware and software actually in parallel. So you don't yet know where application runs on and what actually the performance parameters of your hardware is. So in that time, you still try to define from application point of view or system point of view what resources you are going to need on a rather abstract level. But you don't know what parameters you have to exactly define in the very end when it comes to actually generating a load for IMA module that flies on an aircraft. So it is tackled with the iterative process. That's very common and very natural. So you refine the parameter domain step by step, and then hopefully in the end everything works out well. And then there's, for example, the integration phase where you put all the things together. So you have your hardware, you are going to use the software and of course the configuration parameters you have developed, and you try if everything works. And there where very often errors occur because just of the inconsistency of configuration parameters, for example, within the process. And also you have a rather distributed process which is put or sketched on the bottom of the slide. So on the one hand you have of course a module you want to run your software on or your applications on, systems on. And you have on the one hand side the module supplier who provides the module, provides the capability to do so. You have of course the system designers that define the systems that shall use IMA components. You have the function suppliers, many of them, different of them, and these are usually different companies by the way, who actually provide a system, provide applications, and then on the not last hand, you have the module integrator who tries to actually integrate all of the different parts of the configuration. So, if a distributed process, many actors on board, many interfaces, different tooling, and so on. And our aim is actually to harmonize this process through computer assistant approach by using model-based techniques, especially also with respect to validating what you have actually already configured in the process. So, how did we do it? Nowadays, all these different parameters, they are very often based on tables in the end. And of course, this is very error-prone. And within the Halle project, we first try to harmonize the different parameter domains and the different abstraction layers of parameters by a meta model, which we designed. And I'm going to very briefly talk about this. It basically, so there are, of course, requirements to this. It has to include all the relevant configuration parameters, so it's quite huge in the end for the dedicated process steps. It has somehow to encapsulate the different roles, the actors in the configuration process, because everybody has a different view on it, and you don't always have access to the whole configuration parameter domain. For us, it was important that we actually tackle this at aircraft level, because from, for example, I don't know, module supplier point of view, let's say you are more focused on one type of module, but from a system point of view, of course, you are using different modules. So you want to actually harmonize the configuration across different modules, and that everything which goes out of one goes into another one, and so on. We wanted, of course, to consider standards that are out there and commonalities. This tool is especially designed to be module supplier independent as far as possible, because already the step from A380, for example, to A350, we have introduced a lot of new modules, a lot of new parameters, a lot of new tools, and so on. So it should try to avoid all the different aspects, very special aspects, which you have to take into account. And of course, it should be extensible to future needs. Sounds very challenging, and it is, in fact, because in fact, for this scope, there is no standard available, basically. So there are some ideas, for example, the ARIN 653 standard, but they are not sufficient to cover, for example, if you allocate resources on modules or like. So we have developed our own meta model, and we try to do it in an object-oriented approach, so that you have a, let's say, pluggable configuration structure, which is shown briefly. It's way far from complete on the right hand side, but it forms somehow a configuration tree, and you're using object-oriented matters so that you can actually bind together all the different elements. We make use of abstractions, of libraries, and so on, all the whole stuff, and it covers all the different module types that we are using in the Halle demonstrator in the Halle project. And in the end, we try to be as compatible as possible to A653 standards which are out there. So, to remind you, it's just a model, it's not yet software, but we are talking about a platform configuration tool, so it should be software somewhere. I'm going to quickly introduce this. The platform configuration tool, it targets exactly the nowadays mostly manual and therefore also error-prone, of course, process. No worries, it is safe because, of course, you have a verification phase where you would find any errors in the configuration process in the integration. So in the end, it is safe. But of course, you want to avoid the iterations which are caused by manual errors, for example, by human errors. So it should help you with the specification of those configuration tables, with resource negotiations, and to basically, one example, to create the ICD documents, so-called ICD documents that you need for systems to run on IMA. Of course, you want to import and export what you already have. It's clear, nothing special, and very important, you have to have a very early validation across the configuration parameter domain you have in the process. I've talked about this, by the way, in the last Halle workshop, so I'm skipping this, but you can trust me, it's working rather well. And of course, you want to visualize complex relations. So on the right-hand side is an image about how it looks like. So you want to have, just for this scope of configuration, you would like to have a one integrated tool instead of many, because nowadays there are many, many tools available you have to use to form a configuration across systems at aircraft level. And it should, of course, integrate with other tools which you still need to use, of course. For example, tools provided by the module supplier. So, just for the scope, it is dedicated to support mainly airframer, the activities of the airframer, which is usually, for example, the module integrator, and of course also the function suppliers, which have to somehow cope with all the different tools and bits and pieces. But it is not a replacement for qualified tools. It can't be. So how did we do it? So we have, on the one hand side, when we started to schedule requirements, somehow it turns out everything must be flexible, because everything can change. You have a parameter there which may change in the process because of new definitions, new modules, new possibilities, and so on. That's a programmer's nightmare in the end. So how do you tackle this? And we try to tackle this by model-based approach in the end. So we made a software which is based on Eclipse, extensible through plugins, and we used quite a lot of modern software frameworks for that. On the right-hand side, you see the layers of the software. So we have different layers which are on top of each other to try to be quite modular, so that you can, exchange, for example, the persistence layer if you want to save not to file but to database or like, and many interfaces to actually bring functionality into the tool, and functionality is provided via plugins. So how did we do it? I would like to introduce, let's say, kind of a morphable software through code generation in the end. So the model behind is based on a technology called Eclipse Modeling Framework, provided by Eclipse. It's standard, very well known, very robust in the Eclipse community. And this actually provides you not only with the capability to model your configuration parameter domain, but also to translate your meta model into code in the end. And this allows for fast adoption cycles, for example. If you need to do a change, you can model it, press the button, and you basically have an update of your software that's really needed. But for us, what was most important, it also allows for customizations, for a lot of customizations. And we are using it to basically create all the lower levels of the software. And how does it work? You basically have two type of items. So you have on the one hand side, the meta model, which consists of a so-called eco model. I'm not going into detail. It basically describes what you actually want to have, so what parameters you do, and then a generator model, which describes how you're going to use it. So here you could, for example, also embed not generating code for Java, but for anything else, like theoretically like another language. And then it goes into tools which are provided, JET-Emitter and Java Builder tools, and here comes into play that they generate the code based on templates. And we have used these templates exactly to generate not only the standard interfaces you get with the framework, but also the interfaces you especially need for the configuration platform, for the platform configuration tool. Then you get Java code, and well, basically you can merge this with existing code, and then you get, in the end, a piece of software. So that's how it works. For us, it is important to say in this community, this should not be qualifiable, because it is very clear that to qualify such a piece of software would be impossible, more or less. Well, what did we achieve within Ashley? We have identified all the data flow and workflow for the so-called enhanced process, which is defined in the Ashley project. We have developed this meta model for the platform configuration data we are going to address, and which is used in the demonstrator, in the Ashley demonstrator. Validation, I've talked about already. We are still implementing the interfaces to all the other tools. If you remember the first slide with all the different tools, so this is still an ongoing topic, and visual representations are nice, of course. You need it to analyze the data. It's there. the interface, there will be another speech by Jose, I guess, I don't know, from GMV, which will talk about how actually the interface between all the different tools will work and what we have developed in Ashley. So we are connecting to this. You will hear about this in a minute. Anyway, there's one special tool which we have in our house as well, which is a tool to actually optimize IMA architectures. So this is used very, very early in the process, where you actually would like to know, well, how should my modules look like, what topology would I need, and how would the topology look like if you optimize it, for example, with respect to costs and so on. And as we have both tools in-house, and we are addressing interface between tools, we had a look at, well, how well would this work, because both tools are based on a meta model. Could we use a model-to-model transformation as it is used in many other aspects? How does it work out in the end? Well, it turns out that on the one hand side, if you do architecture optimization, you have a very generic module type. So you don't even know, most likely, what exactly those modules have. And you have abstract link types because you're not interested in all the details of the parameters. You are interested in what type of cable, what weight you have, and so on. You have a very simple routing, so there's not the full, complete routing which you have in the final product, and of course use it very, very early in the process. On the other hand, if you go to the platform configuration tool, you have of course then to create configurations for specific modules, exactly the out channels you're going to address, full detailed routing, signal routing, a description of signals, and this is used very late in the process. So it was interesting to see how does this work out, this interface. And why? Well, the idea was, on the one hand side, in one direction, you could auto-generate IMA configuration stubs, I call them. So there are already many informations in it, which, as you design your architecture with it, which are relevant for the configuration afterwards. And these are time-consuming if you don't reuse this information in the end. And on the other hand, which may be less important but still interesting, is that you could retrieve architectures out of configurations in the end to maybe optimize an architecture if you're updating an aircraft program, for example. How does it work? As I said already, we tried model-to-model transformation technologies to see, and why? Because if you use model-to-model transformation, it would be an error-free transition of information. So there's no human in the loop who can make errors. If your transcription definition is correct, you transfer exactly what you want to do. So as I said already, both tools are based on the same platform, on Eclipse, and both frameworks share the same meta modeling language. So there exists tooling already, and we use tooling which is available that allows you to create such transformation scripts, such tools to actually transfer between two meta models. So we had tried out different approaches with respect to that, and some of them, for example, are also file-based and XML-based. It didn't work out quite well, but of course, most convenient were to use the ones that are based on meta models itself. And how could you integrate it? Once you have such a script, such a transition definition, you could generate code of it again and integrate it as a plugin into your software. So if you have both tools in one computer, in one piece, you could then automatically transfer the information. What was the result? Well, we investigated possible parameter transformations that are possible at all. As I said already, there's no one-to-one relation between parameters, and they're very abstract on the one hand side and very concrete on the other side. We analyzed the transform architecture to configuration and vice versa. And we developed several transformation scripts to see how it works out. And in the end, we ended up with the language that has most benefits, which is the query view transformation operational language. It's available in Eclipse, and it's dedicated for meta models based on eCore. On the right-hand side, you see how we tackled this. So we try to analyze, okay, if you have an architecture, what parameter maps to what in a configuration step, and how would you translate it if there's no direct link? And what is the result? Well, it turns out, of course, by design, a one-to-one relation is not possible. So this is, you won't have a round robin if you from architecture configuration and back, you will lose information. Why is that? For example, from the optimization tools or from an architecture tool, devices are simply identified by a string. And that's basically it. So you don't have dedicated device classes. So, of course, in the platform configuration tool, you have specific device classes. So how would you transfer it exactly? You only have a name and a string. So it means you need, for example, some naming rules to introduce some naming rules that you can exactly transform the concrete module then in the end into the configuration world. For the way back, for example, there's an example that in the architecture tool, of course, you're interested in where are your modules located, where's the peripheral sensors, actuators are located, because you want to know about the cable lengths, which is weight, and you want to optimize weight. So you have for every component, you have, for example, an XYZ axis where it is actually in the aircraft. For configuration, this is not relevant, and so you don't have this information. It is simply missing, so that is something which you would lose if you or which you wouldn't have if you transfer from configuration to platform optimization tool. So, but in the end, it is very clear that this is better than starting from scratch, because still with these items you can transfer quite a huge amount of data. And if you consider that you have a lot of modules in an aircraft and that you have at architecture level already more or less the equipment completely defined and also the routing path, you can still create a lot of configuration steps from scratch through transformation. So it looks quite promising, although it's not complete. Okay, so this was one idea. So this is one trial to give you an idea about what we are working or what we are doing with an Ashley. To conclude, I had introduced quickly the configuration process within an IMA world. So there is a requirement for harmonization between the tools, and I think this is ever increasing with all the different technologies and new modules that are on the horizon. I've shown how we tackle it with respect to platform configuration tool. I think there will be a presentation after me sometime, which also tackles this more from a point of view on a function level. We have used modern software frameworks, and then I've highlighted one aspect, what you could do if you have model-based approaches in several tools using a model-to-model technology on an example. Okay, and I think that's the end of my presentation.